It's great to be here. I wonder if I've given myself a little bit more rope to hang myself with, but we'll see. Okay, so algebraic geometry is a subject with a very long history, so let me start with that. It starts with the Greeks, who were interested in conic sections. Not sure how to pronounce that name, Menachmus, I suppose, studied conic sections in the 3rd century BC. So that's a cone. It's sort of like an ordinary cone, but you take a line and rotate it around a point. So there are various possibilities. You could take a horizontal slice and you would get a circle. If you slightly tilt that, you get take a small perturbation of that horizontal slice, then you get an ellipse. On the other hand, if you took a vertical slice, so that's just a plane, through cutting the cone to get a cross section, you're going to get a hyperbola. Very special sort of slice. If you I call it a diagonal slice, but it's a very special angle, you're going to get a parabola. So as a hyperbola can be degenerate to a parabola. And there are two other more degenerate sort of configurations. If you took a vertical plane, but that goes through the vertex, the obviously the special point of the cone, you're going to get a pair of lines. And then the final configuration, which is somewhat similar to the parabola in the sense that the plane that you're cutting with is at a very special angle that also goes through the vertex of the cone, then you'll just get what I'd like to call a double line. Because if you imagine moving the plane around, you'd see those pair of lines degenerate to that single double line. Okay, so that was the perspective of the Greeks. Of course, we have a quite different perspective nowadays. And that's the algebraic perspective. So I study algebraic geometry, so it has two sides of one coin, the algebra and the geometry. And so the algebraic perspective is that you should think of a conic section as the solution of a quadratic equation in two variables. Let's call them x and y. And then there's a bunch of possibilities. You get the circle x squared plus y squared equals 1. That's the horizontal slice. The ellipse, typical thing would be you perturb at least one of the variables, so the x squared divided by 2 instead of x squared. Hyperbola, quite different. There's a minus sign corresponding to the vertical slice, I guess. The parabola, which is sort of degeneration of the hyperbola, y equals x squared. Pair of lines, which is, you think of it as quadratic, is x squared minus y squared, and you can factor that. And so if you set that thing equal to 0, one of the factors has to be 0, so that's two lines. And then finally, the double line, which is, if I think of it as a quadratic, it's x squared equals 0. So the advantage of this algebraic perspective is that it unifies the sort of perspectives that the Greeks had and offers the opportunity to consider some more complicated examples. So what are the sort of more complicated examples that people consider? So we can increase the degree of the polynomial. So for example, if you go from degree 2 to degree 3, so you still got the same number of variables, x and y. Of course, we get cubics instead of conics. There are three possibilities. Let me see if this pointer works. A cuspidal curve, the y squared equals x cubed. So we call it cuspidal because that point is think of it as being a cusp. Less degenerate would be a nodal curve, y squared equals x cubed plus x squared, sort of comes down, goes around if you sort of try and parameterize it. And then the most sort of typical case, which looks kind of surprising, is that it's actually got two branches. There's this piece and this piece. So somehow you could sort of you could imagine sort of a family of curves degenerate into a cuspidal curve. As you can see, these things get quite complicated quite quickly, which is one reason why the algebra is so useful. In fact, of course, Newton was very interested in conics because conics describe the motion of the planets, but he was also interested in algebraic geometry as well. And he tried to classify cubics. He was interested in all the possible different shapes you could get, roughly speaking, topological types. I've given you 3 of them. He said there were 72. In fact, he made a mistake. But, you know, if you discover the calculus and you discover the universal law of gravitation, you're allowed to make some mistakes. Yes, so, but as been already mentioned, what's maybe more interesting from our perspective is to increase the number of variables. So let's say we go from 2 to 3 variables. In this case, we get surfaces instead of curves. So I've given you some examples there. What the Greeks were interested in, the classical cone is in fact given by a polynomial equation in 3 variables, but it's quadratic, x squared plus y squared equals z squared. Something a little bit nicer, xy equals zw. This surface is in fact, I mean, this point is obviously a strange point. This surface is actually has a rather rich geometry. It's not clear from the picture, but it's actually got lots of lines in 2 directions. It's in fact the only surface with such a property. And then I've given you a picture of the Klebs cubic. But, oh, by the way, these things stretch to infinity, but of course you sort of take a cross-section, you cut them off so that you can get a picture of what they look like. So this is called the Klebs cubic. I have not written down its equation because it's actually quite a complicated equation. So this is sort of to go from what Newton was interested in to this story is actually, again, a jump in time. Cayley was the first person to discover the 27 lines on a cubic surface. This was considered a huge breakthrough. Somebody called this one of the most fundamental intellectual achievements of mankind, which I think is a little bit of hyperbole, but anyway, obviously it was considered a big deal at the time. Let me show you a picture of the 27 lines. So yeah, each one of those kind of curves is actually a line, and they're the only lines on this surface, and there are in fact 27. It's actually, if you sort of go to a science museum, you often see plaster cast models of these things. I know there's a plaster cast model in the Boston Science Museum. There's also, math departments often have plaster cast models of these surfaces. I know the department at MIT had one. And to be honest, sometimes I would just go and look at the plaster cast model and actually check there were 27 lines. It was made easy because each of the lines was, you know, they actually had a label for each line. Let's see. So in fact, as already mentioned, I'm actually interested in what happens in higher dimensions, not just curves, not just surfaces, but what happens in higher dimensions. So you'd have to increase the number of variables and the number of equations. So that's where things start to get a little bit more complicated. So if you increase the number of equations and variables, for example, you could go from 1 equation to 2 equations if you had 3 variables, and then you would expect to get a curve in space. Let me give you two possible examples of that. You could take plane sections of the conic, give conics in space. That's actually not so interesting because somehow they're just still plane curves. The first sort of non-trivial example of that is what's called a twisty cubic in space. It's actually often studied, you often see pictures of these things in calculus textbooks. Okay, let me add my own hyperbole. So I think sort of one interesting future challenge, as already mentioned, as we're supposed to sort of talk about future directions, might be to solve these equations, both theoretically and practically. They sort of turn up in many different contexts, economics and biology and chemistry. In fact, I gave a talk in some location somewhat similar to this, and somebody came up to me afterwards, and a chemist, and gave me the equations he wanted to solve. I should say something, I'm not at this side of the story, so it's a very interesting part of the algebraic geometry, but I don't actually, that's not the sort of thing that I'm actually interested in. So, but anyway, many of the interesting practical applications of algebraic geometry do involve solving such systems. Okay, so what am I interested in? So as sort of mentioned if you were at the dinner yesterday, or Saturday, I should say. One sort of place where the geometry comes up is this idea of painting perspectives. So a picture is a two-dimensional representation of a three-dimensional world, of course. That's supposed to be a cube there, and then that sort of plane is supposed to be the canvas, and there are all those points are supposed to be where the observer is, where the painter is. So the painter looks at what he wants to paint and puts paint on the canvas accordingly. As I sort of mentioned on Saturday, painting perspective is actually not a sort of intuitively easy thing to do, and to sort of practice this, people actually physically made pieces of string and connected them to see what was going on. Anyway, so light travels from the object you're painting to the painter and crosses the canvas at some point. So, of course, light travels in straight lines. So there's a line from the painter's eye to the object, and this line crosses the canvas at some point. Okay, so that's sort of a very practical perspective of someone who wants to paint. But if you're a mathematician, there's something you sort of realize which is not so much to do with the actual this sort of thing. Well, okay, so geometrically we are projecting from a point the painter's eye, so that's still okay. But the point is that from the point of view of a mathematician, there's one point of space that's very special in this picture, and that's where the painter's eye is, because to every point of space you associate a point at the canvas. You can associate points in front of the canvas, behind the canvas, anywhere except the painter's eye itself, because it doesn't really make sense to say to connect there's no line from the eye to the eye, if you see what I mean. So one sort of language to talk about all of this is algebra. So let me describe that a little bit. And to make things easier, let's just drop the dimension down by 1. So let me give you the mathematical perspective. So project from a point, so why not the origin? So that's going to be this point here. And then this green line is like the canvas. And then these lines are just sort of various lines of sight. And so you connect every point to a point of the line. Call that the line. Let's call the line x equals 1. And then what you notice is that the point on the point you get, the point Q you're going to get on this green line, well, its first coordinate is, of course, 1, because you're on the line x equals 1, and its second coordinate is, in fact, just the slope of the line connecting the origin to the point xy. Okay, but the thing to, whoops, pressing the wrong thing. But the thing to realize is that, you can sort of consider various possibilities. This horizontal line goes to the point 1, 0, because it's got slope 0. Even vertical line is okay. Just send it to the point 1 infinity. It looks a bit strange, but that's actually okay. Again, it's like the painter trying to represent the world. How does he represent his own eye? Where do you send the origin? Where do you send the point 0, 0? So this is a story that very much involves Japanese mathematicians. So let me give you a Zen-like question. What is the slope of the line connecting the origin to the origin? So that's the sort of geometric sort of question. So equivalently, what is the slope of the line? That would be the ratio 0 divided by 0. And by the way, that's the ratio in birational geometry. So birational geometry is all about sort of resolving these problems with ratios, 0 divided by 0. And so the solution, there's a sort of mathematical solution to this, mathematical fix. We construct a new surface. So the new surface is this surface over here. And so the old surface was this thing here, just the ordinary plane. The new surface is this surface here, where you've added a line, the red line, sitting over the origin. So if you can't say what the ratio 0 divided by 0 is, just take all possible slopes at that point. So there's a sort of typical word we use for that. We call this blowing up the origin, not in the sense of some sort of explosion, but in the sense of sort of inflating something, like inflating a balloon. So if you took the point, just inflated it, you get a line. So that's called a blow up. There's a sort of stupid joke about this. If two algebraic geometers or two rational geometers are at the airport, they have to be very careful not to start discussing mathematics. Okay, so the Italian School of Algebraic Geometry, so this is around the turn of the century, developed a different approach to understanding algebraic varieties, so solutions to polynomial equations. So this method relies on the process of taking a surface and blowing up and blowing down lines on the surface. So blowing down, again, is like deflating. For example, here's how they would describe the 27 lines on a cubic surface. So this was sort of a new perspective in the whole subject. So it turns out that if you take one of these plaster cast models, when you take the Klebs cubic, and you can pick 6 skew lines, 6 lines in space that don't intersect each other, lie on the surface. And in fact, if you can blow them down, you can deflate all of those lines, as it were, and get the ordinary plane. And then the 27 lines on the Klebs cubic, well, there are the 6 original points. So when you inflate those, they become 6 lines on the surface that don't intersect. There are the 15 lines you get by connecting 2 points, 2 red points. 6 to 2 is 15. And then, in fact, there are conics. Turns out if you fix a point, there's 6 conics through the remaining 5 points, and then 6 plus 15 plus 6 is, in fact, 27. So it's a rather sort of clever sort of way of describing these 27 lines. Okay, so what I'm interested in is what happens in higher dimensions for threefolds and beyond. So quintic threefolds in 4 spaces, for example, this is one very interesting case defined by a single equation. The reason why this is interesting is it's like the cubic. So here's an example of a quintic threefold. It's degree 5 equation. The reason why that's so interesting is that because there are finitely many lines. Before there were 27 lines on the cubic surface, now there are 2,875 lines. That many conics, that many twisted cubics, ... This is actually interesting also in physics, not just in mathematics, but that's another story. Let me ask one question that seems kind of innocent. I say ... Question is it true that in each degree there are only finitely many such curves? This seems like an innocent question, but it's in fact a very hard problem maybe that will be solved in the next 10 years and maybe not. Very interesting question, in fact. So a new feature in 3 dimensions is that you can blow down a line. So you have a single curve on your threefold. You can contract it to a point, deflate it, and then reinflate it in a different way, blow it up in a different way. And this is a fundamentally new geometric operation in rational geometry, which is called a flop. It only appears in dimension 3 and higher. It's not something that happens for surfaces or curves. Oops. And then there's something closely related to these, which are called flips. There's actually a reason for the notation. Flips are sort of directed, flops are not. And then here's a very schematic picture of a flip or a flop. You sort of take the red curve, contract it to a point, and then replace it by the blue curve. And then the rational geometry is the connection between these 2 threefolds. So in this threefold, you had a curve, you removed it, and you put it back in a completely different way. And that's somehow a completely different sort of operation to what happens for surfaces. Here is a question that I've always interested in as we're going along. I think this is going to get more and more abstract. So blowups first appear in dimension 2, flips and flops in dimension 3. I always wonder if there's sort of more to this story. Is there something new that only appears in dimension 4 or maybe dimension 5? If so, nobody's discovered it yet. Okay, so Shigefumi Mori in 1980 introduced a program to generalize what the Italians had done at the turn of the century. He called it the minimal model program. It actually is, he thought of it as really an algorithm, this program as in computer programming. The idea was to start with a variety, something defined by zeros of polynomials, and repeatedly blow down, if you could, surfaces to points on a threefold, or replace curves by other curves, lines, planes, there will be lines and planes, until we get to an algebraic variety with a simpler geometry. Oh, I see, there's something. I made a small adjustment that isn't here. So he, in his sort of monumental work, he constructed flips for threefolds purely by sort of classification. So what I did with Christopher and two other co-authors, Baker and Cascini, we finished Maury's program in Maury's program in all dimensions. That's what the existence of flips and termination in some special cases. So it's an algorithm, so it could potentially loop forever, and of course that's not very interesting. You want your algorithm to stop. So one future problem would be to show that this program works in complete generality, so that algorithm terminates, that there is no, you can't infinitely loop forever, that you can't. So the thing is that it's easy to see you can't keep blowing things down, but you might keep flipping a curve. And then another major outstanding problem is to prove the abundance conjecture, which I'm not going to tell you what it is, but it would give you precise information about smaller dimensional varieties. And so somehow the philosophy of the minimal model program is to take a variety and to understand it by breaking it up into simpler pieces. Okay, so now let me talk a little bit about future directions in the last couple of minutes. So the minimal model program is a very powerful tool to understand algebraic varieties. So one thing that's sort of interesting recently is that we've begun to realize that the ideas behind the minimal model program, if not the techniques, the ideas can be extended to other geometry, other contexts. One of those is Kähler manifolds. So those are sort of geometric objects, but they're not defined by polynomial equations. And it's very surprising, but it seems that MMP works in this case, minimal model program, by the way. Characteristic P geometry, which is even more surprising, that we place ordinary numbers by numbers modulo a prime, call it clock arithmetic. So in clock arithmetic, 9 plus 5 is equal to 2 modulo 12, because if it's 9 o'clock and it's 5 hours later, it's 2 o'clock. I should just say, that's very surprising again because, well, obviously algebra changes very dramatically if you work modulo a finite prime, and so does the geometry. And another context in which MMP seems to apply is foliations, the study of vector fields. So this is a sort of picture of a vector field. And again, that's very, very surprising that this should work. Somehow this shouldn't work, but it does, which is very exciting. And then finally, another future direction would be moduli. So I guess I have to say this very, very quickly. So varieties are often parameterized by continuous geometric invariants, radius of a circle, so that's a bunch of concentric circles of different radii. Then another thing is that in projective geometry, 4 points in a line have one invariant. If you keep projecting 4 points, you can take them back to, 3 points. You can take them back to any other set of 3 points. But 4 points turns out to have one continuous family. So these invariants are often collectively called moduli. This means the collection of varieties with a given shape forms one continuous family. But the thing that's very surprising and very interesting is that that family is in itself an algebraic variety defined by a bunch of polynomial equations. And so the moduli space of curves is being very heavily studied. It's one of the most heavily studied objects in mathematics. And then recent progress in this MMP gives us the opportunity to study the moduli of higher dimensional things like surfaces, threefolds, and so on. And to be honest, this subject is so new, we don't even know the questions to ask yet. The only questions we've been asking are the questions we've asked about the moduli space of curves, which is, I think, we can do more than that, but that's future progress, I hope. And then finally, let me just say that this was produced by LaTeX, Beamer, and something called TIX, all these pictures, and the surf, which is the thing that produced all the surfaces and curves. Thank you.
so we have time for a few questions. While the audience is working up their nerve to ask a question, let me ask you briefly a question.
Okay.
You mentioned that the counts of curves on the quintic threefold had some connections to physics.
Uh-huh.
And is the conjecture that you were saying maybe within reach in the next 2 decades something that is already proven at a physicist's level of rigor? Or would you say even to physicists that's an open question?
As much as I can answer for physicists, I think it's a conjecture for physicists. But one of the interesting things is that what physicists realize is that you can do something similar to replacing you can replace the variety by symplectic manifold and deform the symplectic guy and get finite many curves. So somehow, from the point of view of algebraic geometry, they cheated. They changed the question, which is very clever, but it still doesn't answer the question that the conjecture I mentioned. So yeah.
Are there other questioners? Okay, then let's thank Dr. McKernan for a beautiful talk.